Welcome to part 5 of robotic arm manipulation with human experiences and reinforcement learning. In this video, we're going to go ahead and put together our models, which we can then start to incorporate into an agent to take actions on the environment autonomously. So let's dive right in. We are going to create a model.py. And in model.py, we'll need a few imports, as always. So this is where we're going to import torch, import torch.nn as nn, import torch.nn.functional as f. From torch.distributions, we're going to need a normal distribution, so import normal, import OS. We'll need a few constants here. Log sig max equals 2, and log sig min equals -20. All right. We are going to declare a weights init method. And for this, we're going to say if is instance of if m, which we're going to be passing in a layer, is an instance of nn.linear. We're going to do torch.nn.init init, and we'll use Xavier uniform m.weight gain equals 1. And this is just to get a nice starting distribution for our networks. So torch.init.constant. And here we'll do m.bias and 0. All right. We're going to need two classes here. We're going to need a policy and a critic. I could say actor and critic, but I'm going to call it the policy because it's the policy for the agent. The agent is going to sample from a policy network. I think that name fits a little bit better for what we're doing. So let's start with our policy. So we'll say class policy is a subclass of nn.module. We'll go ahead and do def init self num inputs, num actions, hidden dim, action space will default to none. Checkpoint dir will be checkpoints, and our name is going to be policy network. All right. We'll call it a super class. Policy self, and call the init method. That gets us all the standard information from nn.module, and then we can go ahead and start declaring our layers. This is actually going to be pretty simple. We're going to have an input layer, a single hidden layer, and then our output layer. So self.linear1 is nn.linear, num inputs, hidden dim, self.linear2 is nn.linear, hidden dim, and then we'll have self.mean linear equals nn.linear, hidden dim, num actions, and self.log std linear is nn.linear, hidden dim, num actions. Okay, we will go ahead and declare, given a name, self.name equals name. We will declare our checkpointer is checkpointer. We'll do our self checkpoint file is os.path.join self.checkpointer and name. So basically we want the policy to know how to save itself, know how to, we're going to be writing a save checkpoint and a load checkpoint, and these variables are so that it understands what it is and can go and save itself off to disk. So, and then we'll do self.apply, and that'll be where we'll use our weights in it. And then we'll do some action rescaling. And here we're going to say if action space is none, then self.action scale equals torch.tensor 1, and the dot there is important. Self.action bias equals torch.tensor 0 dot. All right. And else self.action scale equals torch.float tensor. Here we'll say action space dot high minus action space dot low divided by 2. Okay. And then we'll do a second self.action bias equals torch.float tensor. And here we'll do basically the same thing. Action, actually, let's just go and copy. Much more efficient. All right. That is the end of our init method. So let's go ahead and do our forward. So our forward pass is just going to be self.state. And here we're going to say x equals f.relu. Basically just pass it through the model with a non-linearity, as usual. Self.linear1 state x equals f.relu self.linear2 with x. We will grab our mean is self.mean linear x log std is self.log std linear and log std. We're then going to clamp it. And we'll do our constants here, max, log std max. Okay. And then return mean and log std. All right. Then we will need a sample method to sample from the policy. So def sample self state will be taking mean and log std of self.forward. And I'll go ahead and say that these two blocks of code, forward, sample, sort of the core behind this policy was taken directly from a reference implementation of SAC. I'm not explaining the whys as we go through all of this because I would probably explain some of it poorly. I will link to that reference implementation in the video description, so you have that available to you. And then the same will be true of some of the core SAC training loop as well. Some of that will be borrowed from that reference. So, but let's march on here. So std is log std.exp. Normal. We're going to take normal of mean and std. Xt. We're going to say normal.rsample y of t. We're going to say torch.tanh x of t. Action is yt times self.action scale plus self.action bias. All right, and just making sure that that did get, okay. Samples not accessed, forwards not accessed. Just something feels off. I see what's off. My methods here. So what tipped me off here is as I was typing self.action, it's not offering to autofill. And the color is off here on forward and sample. And what it is that I have them tabbed too far over to the right. So let me tab to the left. And now, as I start typing self.action bias, it happily autofills for me. So look at the tips your editor is giving you. So we're going to say logprob equals normal dot logprob xt. We'll say logprob minus equals torch.log self.action scale times 1 minus yt dot pow. So we're taking that to the power of 2 plus epsilon. We did not define epsilon. Let's go up here at the top. That's another constant. One e to the negative 6. Yeah, I can just leave that alone now. All right. Logprob again is logprob.sum 1 and keep dim equals true. We don't want that to collapse. Torch.tanh mean times self.action scale plus self.action bias. And return action logprob mean. All right, and what you're going to find a little bit later is that we will take the action in training, and then we're going to end up taking the mean of that action, so the most probable action during testing. So that's why we're returning multiple things here. One of these values will maintain a certain degree of exploration, and another one is just going to be, hey, this is the best possible action. Go ahead and take this, when you're validating the network. We're going to override the to method. So self device self.action scale equals self.action scale.to device self.action bias equals self.action bias to device, and then we will return super policy, just so we're still calling the standard to method. All right, and then we'll define our save and load. Self. Oh, I need to spell self correctly. Torch.save, self.state.dict, self.checkpoint file, and def load checkpoint self, self.load state dict, torch.load, and self.checkpoint file. And again, must spell self correctly. All right, that gets us to the end of our policy network. The critic network is going to be a little bit simpler, at least by comparison. So we'll go ahead and say class critic and then .module. We will define our init method here. So def init. We need almost none of what just got autofilled here. So here we need num inputs, num actions, hidden dim, checkpoint dir equals checkpoints, and name equals critic network. All right. We will call super with critic and self. And we do not need either of these things, calling the init method. All right. And we're going to have, so learning with a dual queue network, so having one critic network and then a second critic network that falls slightly behind it, tends to stabilize training. If you only have one critic network, training will lean towards being erratic. And you're going to see it, a lot of bouncing up and down. Sometimes it'll just drastically overestimate or underestimate certain states. Having two networks and having one kind of follow the other tends to stabilize that. That's something you see in double queue learning. It's something you see in SAC. I believe TD3 uses it. So that is exactly what we're going to be doing here. So we're just going to say Q1 architecture. And I'm going to say self linear1 equals nn.linear num inputs plus num actions. And if you think about what the critic does, it's intended to take a model state and the action that was taken in that state, and then it's supposed to produce a score, a critic value for the actor network, for our policy. So that's why here you've got num inputs plus num actions, whereas up here it's just num inputs. This is the network that's going to produce the actions. The critic is the one that is going to judge them. So we'll be passing a hidden dim self.linear2 equals nn.linear hidden dim. And then we are going to go ahead and say self.output 1 is nn.linear hidden dim and 1. And then really we can just copy all of this down to Q2 architecture. And now this is going to be linear 3 and linear 4 and output 2. Okay. Just like before, we need to have, really it's going to be exactly the same code, so let's just go copy it. So we need this block, self name equals name, self checkpoint dir, and self.apply weights init. Okay. And then we're done with our init method, and we can go ahead and declare a forward method. And for will take self, state, and action. Again, a state action pair. We're going to declare xu as our variable for torch.cat state action. And 1. x1 is f.relu self.linear1 xu. x1 is again f.relu self.linear2, this time passing in x1. And then finally, x1 is self.output1 x1. Okay. And then we're just going to do the same thing again. We'll do x2, x2, x2. And then have to change x2 and x2 there as well. Oh, and this needs to be self.output2. So self.output2 and self.linear 3 and 4. So the first block should be linear 1 and 2 and output 1. The second block should be linear 3 and 4 and output 2. And then we are going to return x1 and x2. All right, and then we also can just go and copy again the save and load checkpoint functions. Okay, all of that looks pretty good. I think that is correct. So let's go ahead and start to put together our train.py so that we at least have something to call this with. So there are several Python scripts that you're actually going to have to run directly. There's going to be a train py, a test py, and then a train meta and a test meta, as well as the human control. So we're going to go ahead and do our train.py so that we can at least plug in that model and start to see, if it's working correctly. So let's go ahead and do our imports here. So we're going to import time, import gymnasium as gym, import numpy as np. We will do from gym robotics custom, import robogym observation wrapper, the wrapper we wrote earlier, and from buffer import replay buffer. All right, and we'll say if name equals main. And then let's go take a look at human control.py. We'll need at minimum these 3 variables, and really all of these. So let's just go ahead and grab them and bring them over. We may not need them yet, but they'll be useful in a little while. And I'll bring up the spacing there. And I should have had a double equals. That was a bug. All right, and then we'll also do from model import star. And then I really just want to make sure that there are no errors. We don't want to do anything really with our model yet. So for this first pass, I'm just going to say model, let's see, policy equals policy. And we're going to say 1 input, 1 action, 1 hidden dim, action space none, and then we'll leave everything else default. And then we'll say critic is critic 1, 1, 1, and that should be all we need. And let's just make sure that we can create our 2 objects, and we can. It does not return any errors, at least the initialization worked. All right, I'm going to end the video there. In the next video, we will start to put together the agent that's actually going to use, the buffer, the policy, etc., and start to build something up that we can use to train our models. So I'll see you there.